The Boeing B-17 Flying Fortress was more than just a bomber. It was an icon of American industrial ingenuity and resilience during World War II. Introduced in the mid-1930s and reaching full production by the early 1940s, this aircraft became the cornerstone of the United States Army Air Force's strategic bombing campaign against Nazi Germany. Its rugged design, formidable armament, and legendary ability to sustain massive damage and still return home earned it a near-mythic status. But for the German war machine, the B-17 posed a serious and complex challenge, one that tasked their best engineers with the critical job of understanding and ultimately countering this flying fortress. German experts faced a unique problem: how to pierce the armor of a bomber that seemed almost indestructible. Downed B-17s, scattered across the European battlefield, were scarce but invaluable prizes. Each wreckage offered a window into the aircraft's secrets, the hallmarks of its toughness and its deadly defensive firepower. For German engineers, it became a technological battle of wits to dismantle the mystery of the flying fortress and devise countermeasures capable of turning the tide in the skies above Europe. The B-17 itself was an engineering marvel. It was a four-engine heavy bomber with a wingspan of approximately 104 feet and a length of nearly 75 feet. It was powered by four Wright R-1820 Cyclone radial engines, each delivering around 1,200 horsepower. This power was designed to carry the bomber on long-distance missions at altitudes of up to 35,000 feet, making it a difficult target to reach and intercept. Its maximum speed was just under 300 miles per hour, with a more typical cruising speed between 220 and 230 miles per hour, depending on the specific variant. The gross takeoff weight for later models could exceed 60,000 pounds, and it could carry a bomb load of up to 8,000 pounds, sometimes even more with the use of external racks. But what truly made the B-17 notorious, beyond its sheer size and range, was its defensive armament. A typical late-war model, the B-17G, was equipped with up to 13.50 caliber machine guns. These were placed at strategic points to cover every conceivable approach angle. The gun positions included two in the nose, a powered chin turret that was absent in early variants, dorsal turrets on top of the fuselage, waist gunner stations on the sides, a ball turret under the belly, and twin guns in the tail. All these positions worked in concert to create a deadly, overlapping envelope of fire. This all-around defense is what truly gave the B-17 its famous nickname, Flying Fortress. It was much more than just hard to catch. It was notoriously hard to kill. The German response to this threat was multifaceted, yet it was constantly constrained by tactical and technological limitations. To German engineers and tacticians, the B-17 represented a puzzle that could not be solved by firepower alone. The Luftwaffe's initial experiences in 1942 and 1943 against formations of B-17s were sobering. Fighter pilots quickly learned just how lethal the Flying Fortress could be. The concentrated machine gun fire from multiple coordinated gunner positions meant that any fighter attempting a frontal, rear, or side attack would be met with intense and accurate defensive fire. Standard fighter engagements often resulted in the loss of German aircraft, as the combined defensive firepower and disciplined formation tactics of the bombers made individual kills both rare and costly. When damaged or downed, our B-17s were recovered. Special Luftwaffe technical teams conducted meticulous assessments. They would transport these scarce prizes to test facilities, where engineers exploited every opportunity to analyze the design in minute detail. One of the primary bases for this technical study was the Rechlin-Leertz airfield, the Luftwaffe's main testing ground. There, technical officers and engineers would strip a plane down to its bones to understand every nuance of its construction and operating systems. From these detailed analyses, German engineers came to admire the robust structure that gave the B-17 its legendary battle resilience. The airframe was built with strategically reinforced bulkheads and cross members. This design prevented catastrophic failure, even when large sections of the aircraft were riddled with bullet holes or shrapnel from anti-aircraft fire. A unique framing system distributed the structural load across the airframe, meaning that damage in one area did not easily propagate and cause a failure of the entire structure. Engine redundancy was another factor that German technicians greatly respected. The quartet of Wright R-1820 engines meant that losing one, or even two, engines in combat was rarely a death sentence. Damage to a single engine might severely reduce the aircraft's speed and altitude capacity, but it often could not stop the plane from limping back to its base. A frustrating reality for the German pilots and engineers trying to find a way to reliably knock these giants out of the sky. Furthermore, the B-17's fuel system was designed with multiple self-sealing tanks, an innovation that significantly reduced the risk of fire from combat damage and further contributed to the aircraft's remarkable survivability. The German engineers were equally impressed and equally frustrated by the bomber's robust defensive suite. They noted that initial variants of the B-17 lacked a powered chin turret, which left a vulnerability to head-on attacks that German pilots were quick to exploit. However, this weakness was rapidly addressed by American designers with the introduction of the B-17F and the subsequent B-17G models. These later versions featured a powered Bendix chin turret mounting 2.50 caliber machine guns that could be operated remotely. This single addition greatly improved the bomber's frontal defense, effectively closing a vital area where German fighters had previously scored early successes. For the Germans, the concentration and coordination of defensive fire was more than just brute force. It was a sophisticated tactical system. B-17Ss never flew alone. They operated in carefully maintained formations, most famously in the combat box formation. In this setup, individual flying fortresses were positioned to overlap their fields of fire, covering each other's blind spots. This formation, flying dramatically, increased the volume of defensive fire that any single attacking fighter would face, essentially creating a moving wall of bullets that made close proximity attacks extremely deadly for the attacker. Consequently, German fighter tactics had to evolve. Spurred by the need to counter this defensive web, Luftwaffe pilots were instructed to use speed and surprise. They initially focused on head-on attacks before the powered chin turret was introduced, and later shifted to attacking from above or below, aiming to avoid the main concentrated lines of fire. The Luftwaffe also began introducing specialized armament, designed specifically for the bomber-killing role. This included heavy-caliber cannons like the 30mm Mk108, which was designed to disable or destroy a heavy bomber with just a few concentrated bursts. Another significant innovation was the introduction of the WFR grade 21, a large-caliber air-to-air rocket. Fighter pilots would fire these rockets in salvos from a distance before closing in for a gun attack, hoping to break up the tight bomber formations or cause significant structural damage from afar. Yet, even with these technological and tactical advancements, German engineers faced immense difficulty in translating their studied knowledge of the B-17 into a decisive technical advantage. The solutions they developed were often partial and imperfect. The structural toughness of the B-17 was not something easily nullified. Penetrating its strong frames and redundant bulkheads required either extraordinary firepower or incredibly precise hits to critical systems like fuel tanks, engines, or flight controls. Achieving such perfect hits was a rare occurrence in the chaos of aerial combat, where speeds were high and conditions were stressful. Adding to the challenge was the human factor inside the flying fortress. Each B-17 was operated by a 10-man crew that was extensively trained to work as a cohesive unit. The gunners communicated and coordinated with each other constantly, maximizing their defensive coverage and muting any potential weak points in their perimeter. This high level of crew proficiency effectively multiplied the bomber's defensive power far beyond the mere count of its 13 guns. From a materials and manufacturing standpoint, German engineers were constrained not only by the limitations of their available technology, but also by severe resource shortages wrought by the strains of a prolonged, multi-front war. Designing or producing weapons capable of rapidly dismantling the flying fortress demanded resources and manufacturing capabilities that Germany increasingly struggled to provide in the later years of the conflict. The American industrial machine, by stark contrast, operated at a staggering pace. Thousands of B-17s flowed off assembly lines each year, ensuring that combat losses were continually offset and that operational pressures on the Luftwaffe mounted relentlessly. The Germans also grappled with the challenges posed by the B-17's extended range and high-altitude capabilities. Many German fighters simply struggled to operate effectively at the altitudes typically used by the fortresses during their missions deep over Germany. This performance gap limited the window of opportunity for successful interception and attack, giving the bomber formations another layer of protection. Despite all these obstacles, the Germans invested heavily in anti-aircraft artillery, known as flak, which became a critical element of their defense against Allied bomber raids. Large-caliber flak guns would create deadly barrages of metal fragments in the sky, designed to disrupt bomber formations, cause structural damage, and force the bombers to scatter or abort their missions. In many cases, German flak batteries inflicted the most significant damage on B-17 formations. However, their effectiveness was still mitigated by the B-17's inherent ruggedness and the skillful evasive maneuvers of its pilots and crews. The Germans also explored electronic warfare tactics, though with limited success. There were attempts to jam radio communications between the bombers, or to interfere with the operation of the B-17's Norden bomb site. The advanced analog computer that allowed for precision bombing from high altitude. These electronic countermeasures, however, were largely experimental and often deployed too late to have a decisive impact. They were less about physically destroying the bomber and more about disrupting its bombing accuracy or its communications within the formation. Despite all the German attempts, the technical deconstruction, the specialized weaponry, the tactical evolution, and the intensive operational adaptation, the B-17 Flying Fortress remained an elusive and formidable quarry. This was not because the Germans were lacking in intelligence or engineering skill. On the contrary, their meticulous study of each recovered aircraft revealed a deep respect for American engineering achievements. But the fundamental design choices made by Boeing's engineers, specifically the emphasis on ruggedness, system redundancy, and comprehensive defensive armament, proved extraordinarily difficult to overcome. The B-17's ability to absorb phenomenal damage without falling apart became the stuff of legend. Stories abound of these bombers returning to their bases in England, missing large sections of their tail, their fuselages and wings riddled with hundreds of bullet holes, with one or even two engines crippled and smoking, or with gaping holes torn open by flak. These were not mere anecdotes, but testaments to a design philosophy where every inch of the airframe was engineered with survivability as a paramount concern. It was a carefully balanced act of weight, strength, and system redundancy that paid off in the skies over Europe. In the final analysis, the German engineers encountered limits they simply could not fix. The Flying Fortress had a kind of institutionalized toughness built into its very steel and rivets. Its size and robust construction made it resistant to the kind of rapid destruction that the Luftwaffe's available weapons could typically impose. German technological efforts, even as they innovated with new weapons, new tactics, and new countermeasures, ultimately worked around these limitations rather than eradicating them. Decades of subsequent study could not erase the core advantage of American production capacity either. The B-17 was built not just to survive, but to be produced in staggering numbers. By 1944 and 1945, it was not uncommon for thousands of these aircraft to fly over Europe on a single day. The immense industrial might behind the Flying Fortress meant that operational losses, however painful they were for the crews, could be quickly replaced. This was a logistical and strategic reality that weighed heavily on German command, who could not hope to match such output. In that profound respect, the B-17 symbolized something much larger than just tactical resilience. It embodied the broader conflict of economies and technologies that defined the air war in Europe. The Germans faced a bomber whose toughness could not be negated with a single counter-weapon, whose massed formations could not easily be broken by lone fighters, and whose very survival was ensured by a mighty, relentless cascade of American industrial power on the home front. This combination of resilience and effectiveness forged an enduring legacy. The German study of the B-17 stands as a compelling case study in the limits of engineering, showing how difficult it can be to respond to a complex and well-executed design philosophy under the brutal and urgent timeline of total war. Their own technical reports reveal a genuine respect for Boeing's achievements, but also a sobering realization: some challenges, once solved by superior design and overwhelming resources, defy any easy or quick fixes. The Flying Fortress's mythic reputation as the bomber that couldn't be beat is rooted not only in dramatic battlefield anecdotes, but also in these hard, cold engineering realities. These were realities that the German experts' invaluable intelligence and analysis could neither overturn nor neutralize during the course of the war. Today, preserved B-17s grace museums and air shows around the world, serving as silent witnesses to this seminal chapter in aerial warfare. Their soaring wings and the occasional thunder of their engines remind us not only of the terrible destruction borne by war, but also of the powerful role that human innovation and determination play in shaping history. When German engineers studied the B-17 Flying Fortress, they unlocked many of its technical secrets. They understood its frame, its engines, and its guns. Yet they faced a problem that their technology and weapons could not easily resolve. Amid the metal, the machine guns, and the motors, what they ultimately could not fix was the very spirit of endurance that the Flying Fortress embodied, a spirit of resilience that helped tip the balance in the skies over Europe forever.